What happens if you open the helmet in space?
If you've ever pondered the curious question of what would occur if you dared to open your helmet amidst the vastness of space, prepare yourself for an eye-opening exploration into the unknown. While the idea of drifting among the stars may evoke a mix of intrigue and trepidation, the reality is both fascinating and sobering.
Here's the catch. This idea is actually far more serious than it may seem at first glance. And what's more, there are plenty of misconceptions floating around about what really goes down. So, if you're itching to uncover the truth behind what truly unfolds when you crack open your helmet in the vacuum of space, then this video is tailor-made for you. To properly address the question posed in the video, we must first grasp some fundamental aspects of space. And the initial concept to grasp is that space isn't cold. This may sound counterintuitive, particularly to those who have been told that space temperatures hover around minus 270 degrees Celsius. However, it's essential to understand that space temperature differs significantly from what we experience on Earth. Let me elaborate on this point. When discussing temperature, we're essentially describing the level of activity among molecules. Higher activity means higher temperature, while lower activity results in lower temperature. The crucial factor here is molecules. Temperature serves as a macroscopic gauge of a substance, representing an average of the energy within its constituent molecules. Everything within our earthly realm that exhibits temperature is teeming with molecules. Even the seemingly invisible air around us is densely populated with countless molecules. So what's the takeaway? In space, the scarcity of molecules means there's almost nothing to generate temperature. It's essentially a near-perfect vacuum. And this is crucial because there are only three methods for heat exchange: convection, conduction, and radiation. Convection occurs when you cook in a pan. The water at the bottom heats up and moves, displacing the cooler water above it. However, this process doesn't occur in space due to the absence of molecules. Conduction takes place when you touch a hot surface and it transfers some of its thermal energy to you, potentially causing burns. Again, this doesn't happen in space because there are no molecules to facilitate it. The sole mechanism for heat exchange in space is radiation, which operates independently of matter contact. If you were to place a thermometer in space, you'd observe its temperature gradually decreasing until it reaches the often cited minus 270 degrees Celsius. This decline occurs because the thermometer emits radiation, which is invisible to us, and consequently lowers its temperature. So, what's the common misconception? Many people believe that in space, you'd instantly freeze. But that's far from the truth. If you were suddenly transported into space, congratulations! You've unlocked a new fear. You wouldn't freeze immediately. Instead, you'd gradually emit radiation, cooling down until you reach the universe's temperature, approximately minus 270 degrees Celsius. However, there's a catch: the sun. Its radiation would heat any part of your body exposed to it, while the shaded parts would cool down. To illustrate, consider the International Space Station's temperature swings from minus 120 degrees Celsius in the shaded areas to 120 degrees Celsius in the sunlit spots. Similar temperature fluctuations would affect you if you were in space without a spacesuit, but the process wouldn't be instantaneous. It would take time for your body to warm up in the sunlight and cool down in the shade. In summary, cracking open your helmet in space wouldn't be akin to plunging your head into a vat of liquid nitrogen instantly. However, that doesn't negate the fact that we'd experience immediate sensations. Among the more than 650 individuals who have journeyed into space, only 3 have met their fate beyond the Earth's atmosphere. These 3 were part of the tragic Soyuz 11 mission. In 1971, the Salyut 1, the world's first space station, orbited low over Earth. A mission, initially Soyuz 10, was launched to dock with the Salyut, but mechanical issues forced the crew's return to Earth. Later that year, a new mission, Soyuz 11, aimed for the same goal. Launched from Baikonur, Kazakhstan on June 6, 1971, it successfully docked with the Salyut the following day after a 3-hour and 19-minute procedure. Cosmonauts on board, Dobrovolsky, Volkov, and Patsayev, spent a total of 22 days in orbit, setting new records for space endurance. However, tragedy struck on June 29, 1971, as the Soyuz 11 began its return journey. During re-entry, communication was abruptly lost with the crew just before entering Earth's atmosphere. The spacecraft landed in Kazakhstan 25 minutes later, seemingly normal from the outside. Upon opening the hatch, rescuers found the crew motionless in their seats, with blue marks in their faces and blood coming from their noses and ears. The cause of death? Asphyxiation.
An inquiry into the accident found that a damaged ventilation valve during re-entry was the root cause. This flaw left the cabin vulnerable to the vacuum of space at an altitude of 168 kilometers, depleting all air from the interior. Tragically, all 3 cosmonauts perished within 40 seconds. They still hold the solemn distinction of being the only 3 individuals to have died in space, above the Kármán line to this day.
I retold the tragic story of Soyuz 11 to underscore that the primary hazard, particularly for humans, in space travel is pressure, which is non-existent in the vacuum of space. The 3 cosmonauts faced exposure to the vacuum, with temperature not factoring into the investigations. Their demise was directly linked to the absence of pressure. The human body has evolved to thrive in the specific conditions found on Earth, where atmospheric pressure constantly compresses us. Once that pressure is removed, issues arise. For the cosmonauts, exposure to space vacuum led the oxygen and nitrogen dissolved in their blood to form bubbles, rupturing their veins, with the brain being particularly vulnerable. Yet perhaps most astonishing is the documented case of a person surviving exposure to vacuum.
In December 1966, NASA was conducting tests on spacesuit prototypes. Using a large vacuum chamber capable of eliminating all air particles, they aimed to simulate the conditions of outer space. Jim LeBlanc, one of the engineers, was inside the chamber testing a suit when, during the experiment, the hose maintaining pressure inside the suit became disconnected. Within 14 seconds, LeBlanc lost consciousness and collapsed. Fortunately, another person present in the test managed to enter the chamber 25 seconds later and provide oxygen to LeBlanc. To this day, he remains the only individual known to have survived exposure to the vacuum of space. In his own words, his last memory was of saliva on his tongue, bubbling and evaporating before losing consciousness.
So, if you're wondering what happens when you crack open your helmet in space, it's not the instant freeze some movies show. Your body temperature holds for a while. The real danger in space without protective gear is the vacuum. Once exposed, gases in your blood form bubbles, blocking circulation and rupturing veins. Most people only have about 20 to 40 seconds of consciousness. After that, it's estimated that you have around 90 seconds before needing recompression, or death becomes inevitable. Space wasn't designed for our survival, but here we are, thriving in it. The International Space Station, a symbol of global cooperation, has been continuously inhabited for 23 years, proving our adaptability to the most extreme environments. We didn't evolve for space travel or interplanetary exploration, yet we push boundaries despite the universe's hostility to life. In the near future, we'll be everywhere in our solar system, exploring every nook and cranny, leaving our legacy among the stars. That's why conquering space matters. Thanks a lot, and see you next time.